Hi and welcome to the Incite My Life channel. Today we're going to be talking about domain and range. So what is domain and range? Well, domain answers the question, how much of the x-axis does the graph cover? So you notice the x-axis is the horizontal line, and range answers the question, how much of the y-axis does the graph cover? And you can see that it's denoted by the vertical line. So let's look at how to identify domain. Now let me give a little disclaimer about this. This diagram that I'm about to show you does not apply to every function. So for instance, there's log functions that I haven't talked about yet. There's possibly some other functions. I mean, we can maybe bring up trig functions, but this is just a general template. So in general, these situations apply, and if you're in maybe like a college algebra class or even, something along the lines of that, then this is going to be very helpful, and you probably won't run into log functions for a while, or definitely not trig functions for a long time either. So just for the sake of the general idea of domain, this is going to be very helpful. So let's start out with our fundamental question. Does the equation contain a radical or a fraction where x is in the denominator? So based upon your answer, that tells us what we're going to do next. So you see, yes, it has a radical. So then we set what's underneath as greater than or equal to 0. So I would make a note of these if I were you, or maybe take a screenshot of this. It says, yes, it is irrational, so then you set the denominator equal to 0. If it has both, then we'll get to that in a minute. And then if it has none of it, then it's all real numbers. So any polynomial like x squared plus 3x plus whatever, all of that is all real numbers. Okay, so let's get right to it. So the domain of radical functions. Let's solve the first one. F of x is the square root of x squared plus 5x plus 6. So our step one is to set the radicand, or what's underneath, as greater than or equal to 0. Now I do want to say that this applies to positive indexes only. So that means that the square root of x is valid only because the default index, it's not written, but you see how in the second part of that I have n root of x. So when it's not written in there and it's just blank, it's understood to be a 2, which is even. So every even root, so 2, 4, 6, 8, any of those, this is going to apply to. So like for instance the cube root, the third root, that's all real numbers. Okay, so just keep that in mind as you go through these. So then step 2, we're going to factor, and we get x plus 3 times x plus 2 is greater than or equal to 0. And then we're going to draw a number line using your two factors, -2 and -3. Okay, and now what we're going to do is we're going to pick test points from each interval. So you see how we can pick a number that's less than -3. So maybe we'll pick -4, and then in between -3 and -2, there's 2.5. And then greater than -2, usually the easiest one to do is 0. And then we're going to work these out. So if we plug in -4 into our function, we find that we get 2 is greater than or equal to 0, which is true. And then if we put in 2.5, we get -0.25 greater than 0, which is false, since a negative number is always less than 0. And then on the third part, we have 0 plus 3, 0 plus 2, which gives us 6, which is greater than 0, which is true. Therefore, we're going to mark the intervals, or the true intervals of the function. So I'm going to denote that in yellow. So these two intervals are the true intervals of this function. So now let's finish off the problem by writing it in interval or set builder notation. So the top there is interval notation. So if we look from left to right, the graph shoots off to the left into negative infinity, but then comes up to -3. And notice we have a bracket on that. The reason we have a bracket is because it's an included value, which means that it would work. If you plug in -3 into f of x, you would get 0, which is good because we're looking for where is it greater than or equal to 0. So that's fine. And then the u that means union, which means bring together the parts while skipping over anything in between. So we're skipping over that interval that's in black from -3 to -2 because it doesn't apply to our problem. And then we pick up again at -2, which is included, and we go to infinity. Okay, now we have the set builder notation. The basic idea behind this is the x in the beginning represents the variable that you're using, and then the rest of it basically specifies where x is going. So x is less than or equal to 3, or x is greater than or equal to 2, which is the two yellow lines. Alright, now let's take a look at the domain of rational functions. So let's look at our function f of x is equal to x plus 2 over x squared plus 5x plus 6. So first thing we want to do is factor. Okay, make sure that you factor, because if you had just set the denominator equal to 0 without factoring, you would have missed that this actually cancels out right here. So the two common factors are x plus 2. So cancel them out, and you get your new equation, which is 1 over x plus 3. And now your rule of thumb is you're going to set the denominator equal to 0. Or not equal to 0, technically. So it's x plus 3 does not equal 0, therefore x cannot equal -3. Why is that? Well, you can never have a 0 in the denominator of a fraction. Watch, try punching it into a calculator or into your phone and see what happens. It'll come up with an error. Okay, now we're going to write this in interval or set builder notation. So since our only restriction is x cannot equal -3, that means that the domain is everything else that's not 3. So in interval notation, it's from -infinity to -3. Notice this time though we have a parentheses around the -3. The reason being is because it's not included. If you plug in -3, you get 0 in the denominator, which is false. Now, the thing about the infinity, that always is going to have a parentheses. And because it's not technically a value, you can't hand somebody infinity. Infinity just keeps going. So that's why you're going to have the parentheses around infinity all the time. Now in this case, it's actually a little bit easier to write this in set builder. So we look at x, and for x is everything that's not equal to, or everything except -3, which is where you just put x does not equal -3 in the set builder notation. Alright, now let's cover the domain of a rational and radical. So these can vary a lot, but let me just give you one example of these. So like I say, it depends upon where it is. If it's in the numerator, then you're going to solve it the way that we're going to do right now. If it's in the denominator, the only thing you have to do is change it from greater than or equal to just greater than. Okay? So let's look at our problem. The square root of x squared plus 5x plus 6 over x. So we're going to factor the top, okay, just like we normally would. And now here's the thing. We have two domains because we have x cannot equal 0 in the denominator, and then we have the domain of the radical function. So now what we're going to do is we're going to create test points and intervals just like we were doing before. So here's our number line and here's our 3 points. Now keep in mind that -3 and -2 are included values, whereas 0 is not an included value. So our solution would, after working it out, of course, it comes out to be from -infinity to -3 included, and then you see from -2 to 0, and then 0 has a parentheses because it's not included, and then 0 to infinity, and then of course you can see where we have the set builder notation. Alright, now domain of most anything else. So I say most anything else because I mean there are certain things like logs, you know, there are certain functions that this does not apply to, but in general, for the most part, you can say that it's going to be all real numbers or from -infinity to +infinity. So anyway, thank you for watching. I really appreciate you coming by to take the time, you know, to look at these. Please feel free to send me a message and say, hey, can you do this? Can you do, you know, this type of problem? Can you cover this type of topic? by all means, send it to me. I'll be more than happy to get up the video and do the explanation. So anyway, I look forward to seeing you next time. Thanks for watching, everybody.